I welcome you again for this second lecture on this course, which is in continuation to the first lecture, where we talk about introduction of earthquake geotechnical engineering. And mostly in this lecture, we are going to talk about the damages, particularly geotechnical damages during the past earthquakes. So let us see that first, what are the major issues during earthquakes. Again, when we talk about major issues here, that means related to geotechnical. So when we talk about geotechnical, the most important is foundations and the surrounding soil, which are subjected to time varying dynamic loads. So, and naturally when this soil as well as foundations, they are subjected to dynamic loads, their behavior is different than what is during the static loads. So, particularly what are the issues which may crop up during dynamic loading? The one is the behavior of soil is normally non-linear during earthquake excitations. Then your foundations or the soil may be subjected to excessive or large settlement. So, this is also one of the issue which we need to deal during earthquakes. And particularly if your foundation is on loose saturated cohesionless soil, then there may be a problem of liquefaction. We discussed already what is liquefaction in the first lecture. If you are in the hilly areas, then or in the sloping grounds, then landslide could be one of the issue which need to be dealt, and that is also a geoseismic hazard as we discussed in the first lecture. Before we go ahead and then we implement what are the theory we will learn during this geotechnical earthquake engineering course. During past earthquakes, there are a number of examples in which foundation damaged, in some cases causing collapse of buildings, bridges, dams and many other structures. These are discussed in next few slides. So, here we are going to talk about damages in past earthquake, and our focus will be on geotechnical damages. First, like one of the seismic damage, one of the example we are going to discuss in detail is from 1964 Niigata earthquake, which was with a magnitude of 7.5. This earthquake resulted in dramatic damage due to one of the geotechnical phenomena, that is liquefaction. When the earthquake struck, there were approximately 1500 RCC buildings in Niigata city, and out of these, normally in the Japan, though there are apartments which are the low rising buildings made of the woods or like lightweight structures. So, we are not talking about those, rather we are talking about reinforced concrete buildings, and out of these about more than 300 buildings damaged during that earthquake. Out of these, about 200 settled or tilted rigidly without appreciable damage to the superstructure. So, you see this slide. In this slide, you could easily see that if I see here, that you could see that these buildings here, this line, first line is almost they are vertically, there is it does not appear there is any settlement or tilt in these buildings. But one of the focus building is here, let me put it here with this highlighted, you could see that this part here. In this case, this is typical example of liquefaction induced bearing capacity failure. Here building kind of toppled down, but there is not much damage in the superstructure. So, here what happened, the foundation of the building failed due to the liquefaction induced bearing capacity failure. So, this was building turned down here. However, there are some other buildings which are still standing like nearby here, but it get tilted, it did not come on the ground, but it is also, so it is issue related to again bearing capacity and settlement of the foundation. So, these are the typical examples of 1964 Niigata earthquake, where foundation either failed or damaged due to earthquake. There is a liquefaction induced settlement and tilting of the building, and this is an apartment building again during Niigata earthquakes. So, you could see that how much it settled down. So, it is zoomed one picture. Then we do have some damage of foundation in the bridges also, that is substructures of the bridges. This slide is from again from Niigata earthquakes, and here lateral spreading caused bridge pier foundation to move, and it get rotated so much that simply supported bridge span fails. So, it is the not only the failure of the span, before that it is the failure of the foundation, and this foundation failure occurred due to lateral spreading, or what we call lateral spreading is one of the phenomena due to this liquefaction induced. So, this is another example of the failure of a bridge due to lateral spreading of the soil, where the abutment buckled, and it is during 1952 Tokachi Oki earthquake with magnitude 8.1 in Japan. We have seen so far damages during the Pars earthquakes. This is one of the good example where this water tank, which is situated on the piles, on pile foundations, survived during the earthquakes. So, this is one of the example which suggest role of pile foundation in earthquake mitigations of foundations. So, this is storage tank which is supported by concrete piles. Soil underneath this tank liquefied during 1995 Kobe earthquake with magnitude 6.9. So, later investigations suggested soil got liquefied, and there are some small minor damage in the piles, but there was no damage at all in the superstructures. So, this example is suggesting, because this tank was on the pile foundations, on the deep foundations, so it survived. If it would be on shallow foundation, and if liquefaction of the soil would have occurred, then this tank would have collapsed. So, this is one of the good example suggesting that it helps if we select the proper foundation, then it may help in mitigation. Then another example from Japan, Higashi Nara viaduct collapse due to foundation failure, which occurred in 1995 Kobe earthquake. So, what you could see here, in this case you could see that there is a like pier got completely damaged, but this is not only the damage in the pier, it again is related to the foundation failure. So, the foundation below got failed, as a result this kind that collapsed the completely pier, this in fact this have come down. So, it pulled down the complete structure due to the foundation failure. Then again the Nishinomiya Bridge approach in 1995 Kobe earthquake, which is also from Japan, 6.9 magnitude earthquake. This example is from Taiwan, which is of 7.6 magnitude Chichi earthquake of Taiwan, and the bridge name is Wuxi Bridge. Its pier get damaged. The kind of damage you could see in the pier, this is basically due to this primary damage, which is due to this what we could say that site conditions was not very good, seismically very active site. So, as a peculiar damage, which is you could see in the piers of this bridge, which is teared apart completely, even it has been made earthquake resistant design. So, if we do not select the site properly, then this kind of damage can be expected, and this we are going to talk about this issue when we talk about local site effects. In the next slide, this is from Bhuj earthquake, and again damage to pier Kafa bridge in 2001 Bhuj earthquake, and these kind of damages are not only from due to the structural issues, but there are issues, there are damage in fact in the pier also. So, they are related to geotechnical issues, which we are going to talk in detail during this course. Then I show you another good point during the Bhuj earthquake. There is a bridge called Rudra Matha bridge, which is sustained the damages during the Bhuj earthquake of magnitude 7.7, and just after the earthquakes it was inspected and it was found that this bridge is okay. So, it was opened for the traffic. Here one of the issue which I am going to discuss is related to geotechnical earthquake engineering. Here you could see this, you have the bridge and then piers are there, but let us talk about the foundation in the next slide. So, one of the foundation below the pier looks like this, and this is the pier, and you have this top of the, like the bottom of the pier there, or it could be this pile cap so what you have here, surrounding soil, these kind of fissures, these kind of cracks in the soil, they are clearly indicating that there was lateral spreading in the soil, means that the soil conditions due to the liquefaction phenomena, it have spread out. However, still this structure or this foundation of this bridge survived, and there was not much damage to this rather than only small cracks in this foundation. That is why this bridge was functional. So, the liquefaction occurs, but still the survive. So, it may happen sometime if properly designed structures, and then they may survive, their foundation as well as their superstructure will survive during the earthquakes. Even the liquefaction occurs then also. Now, this is another example where a bridge got damaged, and this bridge is on the river Palyar river in Kerala, and this bridge got damaged due to 2004 Sumatra earthquake, tsunamis during Sumatra earthquake with magnitude 9. The damage to this bridge is due to the tsunami, not the direct shaking of the earthquakes. So, what we are discussing here is damage due to tsunami, and you could see the first picture, and in fact this photograph is taken by ourselves when we went for the tsunami damage survey in southern part of our country in the first week of January 2005, after this 2004 earthquakes. So, this is near Kanya in Kerala. So, we went from Kanyakumari to this there, it is between Kanyakumari and Trivandrum river Palyar. So, this bridge was connecting two villages called, I think, Killa Manakudi and Mila Manakudi. So, what happens, you could see that in the first photograph you could see only this deck is gone completely, all the span of the bridge is washed away due to the tsunami, and you could see the substructure part where you could see the piles foundation down, and on the top of you have pile cap, and then you have this the span is sitting on the top of it. And one of the span, like in the second photograph from the top, you could see one of the span is here, which is gone. Then you have another span which is visible, which is like floated during this. So, later when we investigated that there was an issue, there was no clamping between the superstructure span and in the substructure, like it was bearing failures between this. So, though the substructure was intact and superstructure got washed away due to tsunami. So, this also one of the issue which need to be taken care during the tsunamis, which is geotechnical earthquake engineering related phenomenon. Now, let us talk about Sikkim earthquake of 2011. 2000 Sikkim earthquake we also visited for the Sikkim during there, and these are the photographs collected by our team. So, there was huge landslide, and during this landslide before the earthquake as well as after the earthquake there was heavy rain in that area. So, this landslide was not only earthquake, but they are coupled with the rain induced as well as earthquake induced landslides. So, this is one of the in the top photograph. What happened? One of the water stream changed its path and it caused lot of damage at downstream where to the villages, and this one of the fellow which is working on here try to like somehow to divert like that or protect their villages by diverting, but it was a huge task, was very horrible. So, this is another second photograph is from southern Sikkim. You know that there are 4 districts in the Sikkim: north, east, north, south, east, west. So, this is from southern Sikkim, and you could see that there are landslides. So, most of the this earthquake epicenter was in the north Sikkim, which is the covers much part of the state, and but damage was all over almost. Then these are the again some photograph from Sikkim earthquake also only. There are failures to the retaining walls in the first photograph. Of course, it is not very much clearly visible, but what I could see here, there are cracks on the retaining walls, and the retaining walls are used to support the foundation, and typically in the hilly areas when the retaining wall get damaged, then their foundation fails. So, anyway, we are going to talk about in this course about retaining walls also. So, that is part of this course, we will talk in detail. So, here you could see the failure of the retaining wall is completely, you could see like inside that retaining wall is completely failed in the second photograph. This is from Sikkim earthquake. Then these are the landslide photographs from recent Nepal earthquake of 2015. So, and you already may be aware about that lot of damage occurs in 2015 Nepal earthquake. Due to earthquake, landslide occurs and it causes damage to buildings, roads, bridges, all things. Yeah. So, I think let me, thank you. Coming to back to historical earthquakes in different parts in more detail what we have talked. The names and magnitude we already discussed, but now let us talk about from geotechnical earthquake engineering point of view. When we talk about Kanto earthquake of 1923 of Japan, there was a deaths of about 1 lakh people died around that damage, and it was a kind of a like of 7.9 magnitude, but almost great earthquake of Japan. There was a damage in Tokyo, Yokohama area in the capital of the Japan, and there was damage due to tsunami in coastal regions also. And that is after 1923, the earthquake engineering started taking a major discipline in Japan. Then you have 1964 Niigata earthquake with 7.5 magnitude earthquake, and their death was reduced to 26 only, but it caused widespread liquefaction. So, Niigata 1964 earthquake is also famous for that. After that, liquefaction studies started worldwide. Then you have Kobe earthquake of 1995 with magnitude 6.9. Death was quite heavy, like keeping in view that Japan was quite advanced in earthquake engineering, particularly at that time, but still death was more than 5,000. And again, this earthquake was also widespread liquefaction and landslides. Recent one, 2011 Tohoku earthquake of Japan with magnitude 9, deaths was about 16,000, and there was widespread tsunamis in Fukushima region. So, why I am talking about all these earthquakes in Japan? Because they have importance from geotechnical earthquake engineering point of view. In all these 4 earthquakes, there are phenomena related to geotechnical earthquake engineering, whether it is liquefaction, landslides or tsunamis. Continue with this, let us see what is the United States. New Madrid earthquakes, which have 3 continuous earthquake of 7.5, 7.3, 7.8, 3 large earthquakes occurred in 2 months span, they are widely felt, and they are famous for ground motion studies point of view, that is also a geotechnical engineering phenomena. So, how that for these earthquake ground motion prediction equation GMPs was developed, and they are still like that research, a lot of work related to these earthquakes. And they are compared, as I mentioned before, this New Madrid earthquake is pretty much compared with our Kutch region, because New Madrid earthquake geology and geotechnical settings are appear to be similar to what we have in the Kutch or Bhuj region of our country. Then San Francisco earthquake of 1906 with magnitude 7.9, and there was deaths of about 700 people. This earthquake is famous for rupture of St. Andrews fault, which is about like 430 kilometer rupture was there on the ground, because it was primary damage due to when you have the rupture of the site, and it produced about 7 meter offsets. Then you have El Centro of 1940 earthquake of magnitude 7.91 with deaths about 9, and there was large ground displacement of Imperial fault. And why this 1940 El Centro earthquake has been used, much used in research and particularly by engineering community, because this was the first earthquake where the acceleration time tree was recorded 1940. So, the first engineering like seismogram was available with this. Then continue with the United States earthquake. We have in Alaska in 1964 with a magnitude 9.2, and that was about 131, and this earthquake is also called the Good Friday earthquake, and it is notorious for liquefaction and landslide. Lot of liquefaction and landslide occurred. Then San Fernando 1971 with magnitude 6.6, and that was about 65. This earthquake from our point of view is famous because there was a near collapse of lower San Fernando Dam, which is lower San Fernando Dam is an embankment dam, earth or rockfill dam. So, that is like you have, so there was there was damage to this dam. So, lower and this whenever the studies comes across about dams, then San Fernando dams are remembered for earthquake. Then in 1989 Loma Prieta earthquake of magnitude 7.1 with a death 63, there was ground motion amplification and liquefaction. Again, ground motion amplification is a geotechnical earthquake engineering phenomena. Of course, liquefaction is also there, so we are going to talk about that. Then recently Northridge earthquake of 1994 with 6.8 magnitude, and that was about 61. There was extensive damage to buildings and lifeline structures. Continue with this. Let us talk about our country, India. As I already mentioned, we do have the Kutch earthquake 1899 in 8, and this earthquake was widely felt. You know that it depends on the ground condition. The similar effect was observed during 2001 Bhuj earthquake. So, whenever an earthquake comes in the Bhuj or Kutch region, it is widely felt like this even like across far away to Bihar and UP, and then even this Bhuj earthquake of 2001 was sensed in Bangladesh also. So, then you have Assam with 8.7, Kangra 1905 8 magnitude, Nepal Bihar, Assam 1950 with magnitude 8.6. So, here this Nepal Bihar earthquake though occurred in 1934. When this earthquake occurred, people do not know what is liquefaction. So, this phenomena, but later investigation, liquefaction term started after 1950s or so. So, later investigation suggested that what happened in 1934 was a liquefaction, which was a geotechnical earthquake engineering phenomena. And these earthquakes of Assam, Kangra, then Kutch, these Assam and Kangra northeast. So, they are famous for landslides, because like landslide occurred during these earthquakes. Koina earthquake of 1967, 6.5, there was damage to dam, but that dam was concrete dam. So, it got damaged during this Koina earthquake. We do have Bihar 1988 earthquake with 6.6 magnitude and dash was more than 1000. Uttarkashi, which is in Uttarakhand, 1991, and there was dash was more than 700 with 6.1 magnitude. Then you do have others like Kilari, which is in Latur in Maharashtra with 6.1 magnitude and dash was more than 10,000, and the reason being that it hit an area which was not at all prepared for the earthquake. This was like most of the buildings was not engineered. So, that was the reason that lot of deaths and damage occurred even with 6.1 magnitude earthquake. Then Jabalpur earthquake 1997, though magnitude 6, it was not very high, but because this epicenter was close to a big city. So, there was deaths, about 38 deaths in the Jabalpur earthquake. Then you have 1999 Chamoli earthquake with magnitude 6.3, where death was about hundreds. This is known for landslides, because in Chamoli earthquake there was landslide, particularly in Gopeshwar. Then Bhuj earthquake of 2001 with magnitude 7.7 and death was about 20,000 in this earthquake, and this is though magnitude was 7.7, but damage and death was like a great earthquake, and it was watershed to cause awareness. Then we do have Sumatra earthquake where tsunami was generated 2004, Kashmir earthquake of 2005 say 7.6 where it is known for landslides and death was about 50,000. Then we do have Sikkim earthquake, as we discussed some of the photographs, there was landslides magnitude 6.9 and death was more than 100. Then we do have Manipur 2016 which was also known for landslides 6.7. So, this was all about our country, but as I mentioned there are earthquake in other parts of the world also. Let us have a quickly have a glance on that. We do have in Italy 1908 with 7.5 and death was about 83,000. So, that was quite like casualty was very high. Chile earthquake of 1960 with magnitude 9.5 is known to be the highest magnitude earthquake recorded so far, where death was about more than 2,000, and this many of the deaths occurred due to tsunami, the largest earthquake recorded so far, and there was widespread tsunamis. In fact, this tsunami they started from Chile and these tsunami waves hit the Japan after 22 hours. So, they traveled through like that half of the globe during this and caused a lot of damage and casualty. Then Chinese earthquake of 1976 with magnitude 7.8 is considered to be the highest casualty earthquake, where the casualties here picked about 7 lakhs, but it is somewhere between 5 lakhs to 10 lakhs, and you know that the figures do not come from the Chinas, and so that was very heavy. It is in about around million. So, this is the highest casualty earthquake so far. Then you have Mexico 1985 earthquake, again 8.1 earthquake of Mexico, dash was about 10,000. But what we are going to discuss about Mexico earthquake is ground motion, local site effect. It is known for local site effect, and which we are going to discuss when we talk about local site effects. Kokaili earthquake of 1999, 7.6 with deaths about 17,000, again known for landslides. Chichi Taiwan earthquake, you just now seen that there was a damage to the bridge during this earthquake with 7.6 magnitude, and death was about 2,400. So, this Turkey and Taiwan both earthquake was very close, they occurred in 1999 and magnitude was also more or less 7.6. Then you have Java Indonesia 2006 earthquake with magnitude 6.2 and death was more than 3,000. So, this was, and then in 2008 Wenchun earthquake in China, where death was more than 70,000, and 2008 was the year when China is there was Olympic games in China, Beijing, there was World Conference on Earthquake Engineering Beijing, and this World Conference on Beijing on earthquake engineering in Beijing was just after this earthquake, Wenchun earthquake, which occurred. So, thank you very much for your kind attention, and this get over with the introductory part of this course with what we have discussed was the many damages during the past earthquakes. So, now we will continue with the first module in the next lecture. Thank you very much.